Welcome everyone. In this video we will use Gauss's law to derive an equation for the electric field created by an infinite sheet of charge. So we have a sheet of charge like this perhaps. I am drawing it with perspective, trying to draw it with perspective. Maybe we have a line of charge and it is uniformly charged. And it has a charge density that we call sigma. And the unit of sigma is, and I denote the unit with putting brackets like this around sigma, the unit is coulombs per square meters. So, if we are interested in finding the electric field, let's say at this point, what is the electric field here? The first thing to realize is, and I will draw a side view of the sheet to explain it better. If we have the sheet like this, and we are asking the electric field here, the key to understand here is the electric field will be to the right. To the right. And why is that? Because let's say that we have a charge here, and we do have a charge here. It will create a field in this direction. And another charge here, well, it will create a field in this direction. As you can see, the up and down components will always cancel each other since we are interested in an infinite line of charge, infinite sheet of charge, I mean. So the only component left will be the horizontal component, will be to the right. Or you can think of it as it will be perpendicular to the sheet of charge. That is a better way of thinking, I guess. So the field will be perpendicular to the sheet. Well, how can we calculate it? We got the direction, but how can we calculate it? And to do that, as I said at the beginning, we will use Gauss's law, which I derived for the special case of a cylinder, or of a sphere, I mean. And I hope to make the proof for the general case in a future video. So Gauss's law says that if you have the dot product of electric field with ds and infinitesimally small area vector, and you take the integral, the closed surface integral, then you get q inside divided by epsilon naught. So to be able to use Gauss's law, we need to decide on a closed surface. And the surface that I want to use is a cylinder. So I will draw a cylinder like this that passes through our point of interest, and it passes through the cylinder, through the sheet, I mean, as well. And it is like this. And its surface area is A. Now, notice that since we drove ds vectors perpendicular to the surfaces, the ds will be like this for the circular area. However, for the side area, for this area, it will always be perpendicular with the electric field. All right, so maybe I could do it with color coding. ds in green is perpendicular with the electric field, which is away from the sheet of charge, which is perpendicular to the sheet of charge. So if we take their dot product, we will get 0 because cosine of 90 degrees is 0. As a result, the side surfaces of our cylinder won't do any contribution to our integral. So we will be only interested in the circles, in these guys. So what is the surface area of two circles? Well, it is 2i. I mean 2a. The surface area is 2a. And notice we can't just say A because the field is also going in this direction. And we are interested in a closed surface. That's why we need to say 2A. So let's get started. We have, using Gauss's law, maybe I should do it here. We have E times 2A. And this is not a dot product this time. So let's not write it, not to be confusing. E times 2A is equal to Q inside. Well, what is the charge that is inside? It is simply the charge density multiplied with the area, because notice the units of our charge density. The area is A. It is divided by epsilon naught. We see that A's cancel, which is great because it was an arbitrary choice that we made. It should not depend, the electric field should not depend on our Gaussian surfaces properties. And we get that the electric field is equal to sigma divided by 2 epsilon naught. This is the magnitude of the electric field, and we discussed its direction. Its direction is just pointing away from the sheet of charge. And it is perpendicular to the sheet of charge due to symmetry. This formula will be very helpful when we discuss capacitors in a future video. Hopefully, capacitors are a circuit element that I will go into more detail in a future video. I hope you found this video helpful and enjoyed it. If you have any questions or comments, please write them in the comment section. I hope to see you in another video. Until then, take care. I know I ended the video, guys, but I just realized a very important point that I forgot to make. Notice that the electric field's magnitude does not depend on how far away our point is from the sheet of charge. So if we draw the line, if we draw the side view one more time, the electric field will be the same at this point, at this point, at this point. It doesn't matter how far away you are from the sheet of charge, and it may seem that it doesn't make sense, but we got the formula and it is actually like that. And the way it works is the electric field lines are all like this, and their density does not change. They always go with the same density. I hope this clarifies, and I hope this is an interesting point for you because it was an interesting point for me.